All right, I am Mr. Shrum, and I'm back with the second part of the interactions of light with matter. And we left off at bending light. So let's learn about how light can bend. Transparent materials allow light to transmit or pass through them. And if we look at transmission, the movement of a wave through matter without its energy being transferred. So think of the wave just passing through. Light always travels in a straight line as long as it moves through the same medium. However, the speed and direction of light changes when it travels from one transparent medium to another. And this bending of light is called refraction. You see how it appears the straw is going this way, and then as if it's bent in the water. That's all because air is one medium that light is passing through, and then water is another medium. And whenever you're going from air to water or another medium to another medium, it will look differently because light is passing through at a different speed and direction. Okay? It's an illusion created by the refraction of light. And if you go to the next page, the lesson activity has a simulation that you can click on and follow the instructions, write down your answers, and that will give you a better clue of how light travels through water differently than air. If you look at this diagram, you see this incident beam, and that just means the beam we're starting out with. And then that is traveling through air in a straight line, but then we hit glass. That's another medium. So that light beam will travel at a different angle and speed. So it'll go blah, blah, refracted once it reaches air again. So light can travel from one transparent medium to another, and when the medium changes, the light travels at different speed. For example, when light moves from air to water, it slows down. The change in speed causes the light to change direction. This bending is called refraction. And refraction occurs when light crosses a boundary between two different transparent mediums. If we follow the path, if you look at the boundaries, that's the greatest change in speed between the two mediums. And the greater that change in speed is, the more it looks like it bends, okay? And not all of the light refracts. If you look at the simulation, some of that light is reflected back. So some of that light, bam, reflected back, and then some of that does pass through and refract. Visible light bends when it strikes a prism. This action is an example of refraction. You're refracting all of the colors within that visible light. The shape of the prism is designed to split white light into the components, so you can see the whole spectrum. The prism works because each color of light travels at a different speed through the glass. The angle of bending at a boundary depends on the speed of light. Because different colors travel at different speeds through glass, each color bends at a different angle when it enters and leaves the prism. Lenses also work on the principle of refraction of light. In fact, a lens is a combination of prisms. If you look at the image, it shows how the lenses in our eyes work. Reading glasses also have lenses to help people see better. So when light rays pass through the lens, they bend and form an inverted shape, or upside down, on the retina of the eye. Then the optic nerve and the brain helps us to see the image in its original size and shape. Pretty cool. Now, let's look at this answer. Question and answer. A goldfish swims beneath the surface of the water in a fishbowl. What's true about the light that travels through the air and reaches the fish? Some of the light is reflected at the air-water boundary. Whenever light is passing through a boundary, some of it is reflected. And then the light that moves through the air-water boundary changes direction. That's also true. Most of the light passes through because water is transparent, but some of it is reflected back into the air. And then as that light enters the water, the speed changes and it bends. Remember. Now this image shows the spectrum of electromagnetic waves. And notice all that visible light that we can see is actually just a really small part of the electromagnetic spectrum. This tiny piece, we expand that into this spectrum. You have the dark purple and blues to the reds. Reds have longer wavelengths, while these have shorter. As you can see, gamma rays, smaller, X-rays, ultraviolet, infrared, and then radio waves have the longest wavelength. The metric prefixes, if you pay attention to those, that will give you a clue as how small or how big the wavelengths actually are. Some of the smallest, nano, micro, millicenti. Some of the biggest, giga, mega, kilo, hecto. So that will give you clues about how long and how big those wavelengths are. So we've talked about visible spectrum, this visible light. Let's see what the rest of the spectrum has to offer. And I think they go over that. Oh, they go over that in this video. So I suggest checking that out and watch it on your own terms. Because it talks about each one individually, and I think that can be a good summary to watch. Science in the news, invisibility. So, invisibility, we talk about it in movies, TV shows, Harry Potter, invisibility cloak. But have you ever written something with a pen that uses invisible ink? When people write with invisible ink, it's invisible under normal light because within that spectrum, the invisible ink isn't picked up. But if you have a light with a certain color and you shine it on it, the invisible ink is actually visible. People have been fascinated with the idea of invisibility for a long time. Most magic include an illusion in which something seems to disappear. Scientists have also tried their hand at magic by creating and invisibility coding. So we can learn about that research in the following activity. If you go to this article, it talks about that new invisibility coding. Let's see. Hazing, how to hide in nearly plain sight. A new cloaking device can hide objects when a light fog is present. So if you read the article, it talks about a cloak that can hide objects in almost plain sight. It only works under hazy conditions like fog, in a cloud, or through frosted glass. So it's not perfect, but go read that article if you're interested, and then answer these questions. Summary, you can watch that summary video on your own. But it just goes over what we talked about: visible light and electromagnetic waves that are not in that visible spectrum. Radio waves, infrared, gamma rays, ultraviolet rays, you name it. They went over this. They went over that in this lesson. Mirrors. There's a lot of stuff in this lesson. So I hope that helped. And I will see you in the next tutorial. All right, take care. See you next time.